So our next subject is going to be the wave function. So we're going to call the wave function psi, and it's going to be a function of both space and time. It can change if you move around in space, and if you just wait and watch it, that'll change too. And the basic idea is if we've established that everything has a wavelength, so there'd better be a wave function. There has to be an actual mathematical function that has that length, and we're going to call it psi. Now psi, the really important thing, big fundamental topic of the idea of this course, is psi is the object. It's not some mathematical representation or whatever. It is the thing. So when we talk about the wave function of a photon, or the wave function of an electron, or the wave function of a proton, that is the photon, the electron, the proton. Everything there is to know about that object must be somehow or another contained in that wave function. Now in this class, we're going to focus almost entirely on what we call the time-independent wave function. So instead of worrying about the wave function in space and time, we're going to focus on the time average properties. So we're going to look at basically what you might call a standing wave. And so psi will become psi as a function of space. And for a lot of the class, we're just going to have one dimension. We're going to start with just x. So we basically have a ruler, a single dimension, and we're interested in how the properties of our thing change along that one dimension. We're going to expand beyond that later in the class because, of course, molecules and atoms aren't one-dimensional objects, so we'll learn how to deal with that. But we'll start with problems that are basically one-dimensional. Now I'm going to start this idea with a really weird one. What is the wave function of nothing at all? That sounds sort of like something that you might encounter if you're reading Waiting for Godot, or in a class in general about Samuel Beckett or existentialists. But basically, what describes nothing? Okay, something that does not exist. And I submit, and it turns out to be reasonably true, that even though it's strange, basically something that doesn't exist is, well, nothing. So that means psi of x is equal to nothing. It's a flat line, dead flat line with a value of 0, and the value of 0 is going to matter. So if it's just zilch, then that's equivalent to something not existing at all. Okay, so if a wave function that is zilch is equivalent to something that doesn't exist at all, then a wave function that isn't zilch, that isn't 0, must have something to do with something existing. So here's a wave function. It's zilch for a while, it isn't zilch for a while, and then it's zilch for a while again. So over here on the left, where it's flat and 0, whatever this thing is, it isn't there. Over here on the right, where it's flat and 0, whatever this thing is, it ain't there either. So that means somewhere here, where the wave function is wiggling and looking like a wave and has values that aren't 0, that must be where our silly little object is. So really, what this turns out to mean is that the object is kind of somewhere in there where the wave function isn't 0. And that's somewhere in there, and what we mean by it is the next thing that we want to begin to think. So it turns out that you can do an experiment on almost any quantum object and find out pretty precisely where that object is, or actually where it was, but that's another one of these Brecht kind of existential deals. So let's just consider for the moment that we can find out exactly where the object, whatever it is, an electron, is in space. Essentially what we're doing is, in this wave-particle duality scheme, for a little bit we're making it be a corpuscular thing, a particle that is more or less at an infinitesimally small point in space. So we have this wave function again that's nothing and then something and then nothing, and where it's something in the middle is where the object essentially is somewhere. And it turns out that we can do an experiment that ends up saying, you know what, it's right there, right where I put this dot, where we're in sort of a negative lobe, the first negative going lobe of that wave function. That's kind of weird, but it turns out to be basically true. So very early on in the development of quantum mechanics, there was this guy named Max Born, and he put forward what we call the Born interpretation of the wave function. And that is Max Born, this German fellow. It has nothing to do with Robert Ludlum or the Born identity or Tom Cruise or anything like that. So we're talking Max Born and the Born interpretation of the wave function. And what Born said is that the wave function will tell us something about the probability. If we do that experiment to find out where that object is or was, then the wave function's got some information in it that tells us the probability of where we will have found the object. Okay? So what Born said was this probability distribution is going to be the magnitude of the wave function squared. And what that means now is the next thing that we have to think about. First off, let's just go see how we go about doing this. So here's a wave function again. It's got positive values and 0 and negative values. We'll make it again nothing on the left, wavy in the middle, and then nothing again on the right. All right? So that's the wave function, psi of x. And the first thing we're going to do is take the absolute value of that and then square it. Why we take the magnitude is something we'll get to later, but when I take that wavy thing and I square it, basically the positive and the negative lobes all become positive. And what you get is this curvy thing like this, basically displaced up from 0, so I've got 0 there as a dashed line. My drawing is pretty rough here, but the really important thing is that all the values of the probability distribution are positive or 0. And that's a good thing because we really don't like negatives. And if we go down here, we have nodes in the original wave function. Now in the probability distribution, we have minima that go down to 0. So there's 1, 2, 3 nodes in the original wave function, and then we sort of have a 4-lumped camel here in the probability distribution, where there's 3 minima corresponding to those 3 nodes in the original function. Okay, so the nodes in the function, which are 0 crossings, become areas where the probability is 0, and near the nodes are areas where the probability is near 0. So the places where the wave function, or the absolute value of the wave function, is large, those are places where we're going to have a large value of the probability distribution. And those are these 4 lumps in the 4-lumped camel. So that, if you do this experiment and go look for this object, those 4 areas are the 4 areas where you're most likely to find the object. Now the next thing we've got to deal with is what we call normalization. What we mean by normalization is that the probability, when I do this experiment, the probability that I find the object somewhere has got to be 1. I've got to find the object. As long as it exists, if the wave function is 0, then it doesn't exist, and my probability of finding it is 0. But as long as it's not that special case, then the probability of finding the object somewhere, anywhere, has got to be 1. So what we're going to do is make that probability distribution. We're going to integrate it over all space, whatever coordinates we have in the system. In this case, x. We'll integrate the probability distribution, which is equivalent to integrating the magnitude of the wave function squared over, again, all the x values, and that has to be 1. So in mathematical physics, we call that normalization, making sure that the function in one way or the other adds up to 1 is a very, very common thing here. So that's a requirement for this wave function. So let's summarize where we are now. So I've got a wave function, psi of x. Let's make it this single node function here, nothing, down, up. There's a node in the middle and back down. Remember again, you need a 0 crossing to have a node. So it's only in the middle there where we really cross 0 that we have 1 node in this particular wave function. So psi squared, which will be the probability distribution, is now going to have 2 humps and a minimum near 0 where that node used to be in the middle. So that node now becomes a minimum value of the wave function. And then we're going to integrate that psi squared, that probability distribution. So let's make a line over 0 here. The integral of that wave function is the area under this curve integrated over all x, so from negative infinity to positive infinity. But really over areas where the function isn't 0 is where we have to integrate. So those are the 3 requirements here. We've got the wave function, it's got positive values and negative values where the object is, and is dead flat and 0 where the object isn't. we have the probability distribution, the wave function squared, which has high values where the wave function has a large magnitude, whether positive or negative. And then we have this requirement that if we take that probability distribution and integrate, the area under the curve of that probability distribution over all space has got to be 1. Now, it's going to turn out that it's a lot easier to figure out the shape of the wave function. We're going to be able to figure out what the wave function looks like much more easily than we're going to normalize the wave function itself. So for the sake of argument, we're going to call this unnormalized wave function phi of x. I'm going to use a few different symbols. And the unnormalized wave function might be little or it might be big. But basically the shape of those two things, if you've got a little imagination, it's about the same. So there's a small function or a big function. So we're going to identify what the shape is, and then we're going to need to figure out how the wave function is normalized. And the procedure is really pretty darn simple. So if that's the unnormalized wave function, psi of x has to be some constant n times phi of x, which is the unnormalized wave function. And we're going to go integrate that over all space. So we have to square the wave function, the phi of x. So we got n squared there, and we've got the magnitude phi of x squared. And then integrated over all space. That has to be 1. So the n squared there is going to come out of the integral. And then just by simple division we get n, and because everything's squared we have to take a square root. So it's 1 divided by the square root of that integral of the magnitude of phi squared, the unnormalized wave function squared. So to normalize an unnormalized wave function, you just integrate that unnormalized wave function, take a square root, and turn it over. Take 1 over the x, and then that gives you the normalization constant n, and you can multiply the wave function by that value. Now it also turns out that most of the time the normalization actually doesn't matter very much. So once we figure out the shape of the wave function, most of the properties of the object aren't going to care about how big or how small the wave function, the overall wave function is. So we get the shape, we turn out to learn most of the things about the wave function. So a lot of the time we're not even going to worry about that normalization constant. So a bunch of the time we're just going to leave it out. But there's always a caveat. Sometimes it really matters a lot. So I'll be very careful to point out where the normalization really matters. And when I say the normalization really matters here, I really want you to pay attention, because it's going to turn out to be something that's important for you to do. And of course it's going to show up on an exam at some point, because when it does matter a lot.